Okay, so I want to show you guys what I want to do today. This is kind of fun talk. So we're gonna.
Look how big my baby shark is.
Wow.
Ew, why would you take that? What are you gonna do with that?
Put it in a jar.
And then what?
Pickle
Look
it?
at it?
I had one of those.
We're gonna
I
make
didn't even
YouTube
fridge it.
videos of it's gonna be a sitcom between different baby sharks.
Oh my
They're
God.
always gonna be the same
Interruption.
thing.
I need to assign more homework to you, honestly. Too much time.
Meeting in the auditorium. At 7th period acting, go to the auditorium.
Okay.
I need to do that.
So here's what I want to do. We're gonna take a day off of. I'll give you a chance to kind of wrap things up on the test, and that's fine. You'll have time. I'll leave that one open for a while. You know, it's, but I want to start, getting back to talking about gravity. Very short chapter, very short. I mean, we won't even do a test on it. We'll just kind of combine it with some other stuff. It'll probably take us about a week to do this. It's really light, but it's very interesting. So we talked a little bit about what gravity really is, right? About gravity wells. Let's go back now and let's kind of take a historical approach to studying gravitational interactions on large scales. So people have, for a very long time, been observing the motions of the planets and moons, or even moons around the planets. People could see that, Galileo was actually, with his rudimentary telescope, could actually see the moons of Jupiter. Not all of them, but some of them, traveling around Jupiter. And so that was pretty profound to see that okay, now, not only are these things then probably traveling around the sun, like us, that must be the case because we can actually see individual moons traveling around that planet. And he got a pretty good idea. He got locked up in house arrest for the rest of his life because of this, because it contradicted church doctrine at the time, and so he got kind of thrown in the slammer. But he had a pretty good idea what was really going on then with the physics of gravity and the solar system. People, in taking careful observations and monitoring the trajectories of the planets through the night sky, noticed some very interesting things. Kepler in particular kind of put all this together. And he noticed that one thing, that the orbits of the planets were elliptical. Okay, so that's one thing that became clear. So let's take a quick look at, I'll link to this too on the website. This is kind of a fun little toy to play with. Where is this thing? Okay, so what we see, and I'm going to actually do Mercury as it really is. That's the orbit of Mercury. If we go back and we look at like the orbit of Earth and we show the other solar system objects.
Wow, we're like, it's in the center for us.
Pretty close to the center,
Mm-hmm.
right? If we go even further out, what if we go out to like Neptune?
Isn't Pluto not a planet anymore?
That gives us, it's not.
Oh.
Solar subject, yeah, that's right.
Is it a moon?
So if we go out to Pluto,
Jinx.
we go out to Pluto. Pluto's pretty eccentric orbit. It's not even in the plane of the other orbits in the solar disk, which means it's probably an accreted planet. It just kind of wandered in and we grabbed it. But what's going on? Including Pluto, there are 9 planets. So there's Pluto, Neptune, Uranus, Saturn, Jupiter. Where's Earth and all those other ones?
Yeah.
Where are they?
Way too close to be shown.
Yeah. So if I go into like Jupiter, let's zoom in a little bit. Only then do we start to see that these other planets. I mean, so you get an idea of the scale,
So
right?
Neptune's like freezing cold.
Yes, literally.
It is
Yeah.
really nice.
And Planet X, which isn't on here, Planet X would be spectacularly far away. I mean, it's much, much, much further than the orbits of any of these planets. Okay, let's go ahead and let's go back to Mercury though, because we're eventually going to talk more about Mercury. So what we notice here is that yes, the planets do describe an elliptical orbit, and we need to have a rudimentary understanding of analytical geometry to appreciate what this is all about. Analytic geometry is now a topic that we don't really cover in schools, in high school. It'll be kind of a college topic for you. But analytic geometry, within analytic geometry, we study the properties of various types of conic sections. And so ellipses, for example, ellipses, parabolae, hyperbolae. We're going to focus on ellipses though, because closed orbits form ellipses. What an ellipse, the way you can create an ellipse with let's say a piece of chalk and a couple nails hammered into a blackboard and a piece of string is very simple. All you do is we put 2 nails, one of them right there, one of them right there. We're going to take a loop of string and we're going to attach the loop of string around the nails, and then I'm going to take a pencil and I'm going to move the pencil around the outside of keeping the strings taut. I'll move it around the outside and I want you to see what happens.
It's gonna match.
Yeah, there are the loops of string, and maybe they'll even, we could even loop it around there, right? Because that's always going to stay the same distance. And what do you notice about the sums of these 2 legs of the triangle that we created?
They're isosceles.
They always equal the same thing.
They always equal the same thing. Yeah, right? So doesn't that make sense then, that this would be, here's my pencil, and there's the loop, and it's going to describe that exact shape. And if I make the ellipse more eccentric, it maybe is a little more dramatic to see, meaning if I make it more, less circly and more ellipsy, to use real technical terms. If I do something like that. Right? See how that works? Okay. So what's special about that other place? The empty focus? Nothing really. It's just a place. But it's a place that it's kind of, there's nothing special there. But geometrically, we need to know where that empty focus is so we can understand that this is an elliptical path.
Yeah.
Okay? So that's Kepler's first law. Planets move in elliptical orbits. Sometimes the ellipses are quite circular. Like if we look at the Earth, for example, it's very circular. Notice that for the Earth, if you look very closely here, the center of the sun, which is at one focus, and the other focus, they're very close together. They're not exactly right though, are they? I mean, it is slightly elliptical, slightly eccentric, we would say, but it's not very much.
Which
Very
which
slow.
planet is the most?
Well, see if you can explain something here. I don't know for sure, but I have a hypothesis that it's going to be probably Jupiter. Let's just see. Oh, I was wrong. I was wrong. Actually, probably there's a reason for that. Because Jupiter is the one that's taken the most hammering during the period of heavy bombardment in the solar system.
Why? I thought it was mostly gas. No, that's sound.
Well, no, they both are. They're gas giants. But because of Jupiter's enormous gravity, it pulls in.
It's the reason we exist.
So
It
we-
is. It's the reason we exist even
Jupiter
today.
is?
Yeah. If there weren't a big planet like Jupiter fairly close to us, we would be at much, much greater risk of large-scale planetary impacts. Right now, I think they happen on average once every, I want to say, gosh, I can't remember what it is. I've read all this. I want to say it's like once every 100,000 years. It's a pretty big. I think.
On
I
us?
was remembering my head was 150,000.
And I think there's like a 1% chance.
Of hitting us?
Well, I want to say it's like the average is once per century of a fairly significant impact. Like there was one, for example, in 1927 in Tunguska, Russia, which was enormous. I mean, I'll tell you what. Remind me
Thank
on
goodness
Friday.
it didn't
Remind me,
rush.
and we'll look at some. I'll show you some stuff about that because it took whole enormous tracts of forest in Siberia and it just flattened all the trees, and it was seen all the way. It was a bright flash even as far away as like London. It lit up the night sky, and it was
You didn't have a huge one, but there was one like what, 3 years ago?
pretty big. Yeah, that one that hit in Russia, I think.
Why does
Wasn't
it
it?
hit Russia
Yeah,
all the
Russia.
time?
I don't know.
Poor
Russia is the biggest country in the world.
Yeah.
people.
But this one actually hit pretty close to. I mean, it broke windows and just the sonic boom. Yeah, it was a pretty big deal. So Friday, that'd be a good day to kind of look at that a little bit.
Wait, if we go to Jupiter, would we just be smashed because of so much gravity?
You'd have problems on Jupiter for several reasons because you'd be smashed. Well, you wouldn't be smashed because of the gravity, but there's nothing to stand on, and so you'd fall towards the center, and the pressures would get so great that you would just be squeezed to death. So yeah, it'd be a bad thing. You would,
So Jupiter is sending it's not.
yeah, it's not very hospitable. We'll go back to Mercury. Okay. Is there any significant difference between what we're looking at now and the orbital mechanics that would describe, for example, the moon's path around the Earth?
Yes.
No.
No.
Mm-mm. There aren't. No, they would be pretty similar. Okay. The moon.
Venus. It says.
It says on there?
I just looked it up.
Has what?
Has the
Venus.
closest.
Look at Venus. That's what it says.
Is the closest to a circle?
Oh, yeah.
Oh, wow, that is close.
Who's the farthest, Pluto?
But it also.
That's not a planet.
So you can't even see the two. I mean, you barely. It's just very, very slightly off. Pluto would be the most elliptical, I would think.
Yeah.
We're that new one.
Would be the most elliptical. Planet X would be, yeah.
How is that in our solar system? You said?
I can't. We'll have to look on Friday again. I can't remember.
Planet X?
Yeah. So
Is it in our orbit?
no, way, way out there. Way out there. So speaking of the moon, there's just a little side note here. How did the moon probably form?
Another hitting a glancing blow with our planet.
Okay, so yeah, what probably happened was, and this is more and more seems to be what the models show is almost certainly what happened. Probably very near the Earth's origin, when it was very, very young, it was hit by a planetoid, probably roughly something the size of Mars. Probably a planet that had previously, it was a part of our solar system, but just got ejected from its orbit by one of the big planets and went on a rogue path and hit the Earth and kicked up a bunch of debris, molten debris, that rather quickly coalesced to form the moon. I mean, I want to say, if I remember what I read about this, I think it was like on the scale of like 1,000 years, the moon was formed. Really, really small time scale, maybe even less. It would have obviously been pretty catastrophic, but there wasn't much around at the time to be susceptible to that. Earth would have been pretty inhospitable to begin with, but it would have liquefied the mantle of the Earth. It would have gone back to being completely magma. But anyway, so what's kind of interesting about that, remind me to talk about this later, we can tell some interesting things about what the moon would have been like at that time, and it had a profound effect on the length of a day on the planet. There's something kind of interesting. So remind me to sometime when we got a good opportunity, we'll talk about how the length of an Earth day has changed during the Earth's lifespan. It's pretty interesting. Okay, but back to business here. So Kepler's first law, planets travel in elliptical orbits.
Mm-hmm.
Kepler's second law, this is pretty interesting, and this is pretty amazing. I mean, not amazing, but it's cool that he noticed this.
How old is this guy?
Kepler would have been...
I meant, was he
Uh,
Aristotle's?
no, way after that.
Okay.
Okay, Google, man. Check it out, Ryan. What was Kepler's...
Why isn't he famous? How
For
come I
some
never
reason I
heard his
think
name?
Oh, you've heard of Kepler, haven't you?
No.
Oh,
Oh.
I think you have.
I think you guys are lying.
So what was noticed about Kepler's second law, what was noticed was that knowing the rough distance from the sun for each planet, being able to measure the rate at which it sweeps out its orbit around the sun, what he noticed was that any object in orbit sweeps out equal areas of orbit over equal time periods, right? So let me demonstrate this.
So that's how we get time, probably.
No,
Okay.
no. But let's take a really eccentric orbit here. And when did he live?
1573 to 1630.
Okay, so
that
quite a
was
while ago.
still a long time.
But even then, he saw this. What he noticed was that if I add...
Oh, speed.
if I sweep out area over fixed time intervals, what do you think is true of the areas of each of those sectors?
They're all the same.
They're all the same. Yeah. So when it's further away, it's moving much more slowly, so it's not traveling as far. It's not traveling through as many degrees of arc, right? But it's a lot further away, and so it's sweeping out more area because it's a longer sector, right? Does that make sense? When it's close, it has to travel quite a ways to sweep out the same amount of area because it's so close that the sector is really shallow, right? But that's pretty amazing that it does that it sweeps out equal areas of arc in equal times, okay? And that brings us to Kepler's third law, which just says, and he noticed this also, that, I'll show you maybe one more thing. Well,
So
show you that.
is the empty focus just where the sun is mirrored on
Yep.
the other side?
Mm-hmm. Where the sun is mirrored, exactly.
First I thought it was the center of the thing, but that's obviously not the center.
No, not the center. So if we look at Kepler's third law, what we notice here is that in this case, P stands for the orbital period and A stands for the radius. So if you look at any planet, what you're going to find is that the square of the period is proportional to the cube of the radius. Okay, that's always the case. So we can do this for this weird eccentric orbit of Venus, or we can do it for Mercury. We'd see the same thing. We'd see the same thing for Earth, and so on and so forth. Okay? So what does that mean? Okay, that tells us something interesting. It tells us that, here's the way we would write that.
B squared equals A plus.
We just write it like this. The ratio of T1 over T2 squared equals the ratio of R1 over R2
So you right?
cubed. Okay? So for example, let's just do kind of a calculation. Let's determine what if we wanted to put a satellite in orbit around the sun, and let's say we wanted to put it close to the sun. We wanted to put it half of our radius away, half as close again to the sun as we are. Does that make sense? So we're 98 million miles from the sun roughly, so we put it in there about 49 million miles from the sun, okay? We want to know how long is it going to take for it to travel once around the sun. What is its orbital period going to be? Okay, so let's maybe change these subscripts, and let's call this S for satellite, and let's call this E for Earth. S for satellite, E for Earth, how about it? Okay. So what is the radius of the satellite in terms of Earth radii? We said it was half as far away, right?
Mm-hmm.
So would you agree that it's just 1/2 R sub E?
Yeah.
Okay. So really all we're trying to do is algebraically solve for the period of the satellite, aren't we? Does that make sense? And this is pretty simple math to do, and we're going to get an answer right away. So if we make this substitution, let's plug that in for R sub S. So then we end up with T sub S. I could go ahead and distribute this power to both parts, right? So I could write that as T sub S squared over, I don't have to. Maybe I won't. I might. There's no reason to do that. I don't have to. So T sub S over T sub E squared equals R sub S is 1/2 R sub E over R sub E cubed. Any algebra I can do there?
Wait, so how did you get the R sub S is equal to 1/2 R sub E?
Because we said that, right? Didn't we say we wanted to put this satellite in an orbit around the sun that's only half as far from the sun as we are,
Okay.
right?
I missed that part, so.
Okay, so that's what we specified. What can I do inside this expression?
Put an E. Oh,
Divide
I
by
see.
three.
Yeah, I can cancel, can't I? Look, I could cancel R sub E. Okay, so it's kind of convenient for us to write this in terms of an Earth radius, isn't it?
Mhm.
So then we end up with, this is equal to 1/2 cubed, which is what? 1/8. Okay, so let's go ahead and take a square root of both sides, how about, right? So then T sub S over T sub E just equals the cube root of 1/8. Well, the cube root of 1 is 1, the cube root of 8 is 2 times the square root of 2.
Right. The square root, right?
Oh, hang on,
You said the cube root.
cube root, sorry, cube root, yeah. So the cube root of,
No, you said the cube root.
oh, sorry, I meant,
Yeah.
I meant square root, sorry. Square root of 1/8, there we go, perfect. Right, so that's 1 over 2 times the square root of 2, 1 over the square root of 8, right?
Yeah.
Which if we want to rationalize that, we could say square root of 2 over 4,
We don't want to.
but we don't want to probably. It's fine. Either way, it doesn't matter, not a big deal. And so all I have to do is multiply each side through by the period of the Earth. So T sub S equals square root of 2 over 4, which is going to be about, so it's going to be about,
Are you doing this in your head?
I'm trying, so it's going to be about 2.8, so I'm going to say about 3.3, about point
9. 3.
0.3 some, what is it, somebody got a calculator?
I said it. Did that in my head. You really impressive.
About,
Can I say 3
Just
seven?
because I could tell he was gonna
what,
say.
what is it again?
0.35.
About 0.35? Roughly equal to 0.35 times T sub E, okay? Well, what is the period of orbit, of an Earth's orbit? What is that?
You said.
What's T
wait.
sub E? How long does it take the Earth to go around the sun?
Oh, 365 days.
Or 1 year, either way,
Oh.
whatever units you want to use, right? So then how long is this gonna take? Well, it's gonna take 35% of a year.
Wow.
How about that? Right?
Yeah.
So we got it. That's it. That's how long it would take. Interesting. I mean, it's not linear though, is it? Right? So we cut the distance in half, but the orbital period didn't get cut in half. It got cut a little more than that, didn't it? Right? Okay. All right. So pretty interesting. Now, what if I told you here though? Those are Kepler's laws, and we can do some more with that stuff. But imagine, put yourself back. You know, go back. Oh, let's say 200 odd years ago. Let's go back 220 years or so. Can you imagine at that time what a daunting task it would be to try to measure the mass of the Earth? I mean, how could you do that? How in the world could you do that? You can't really stick it on a scale, right? What are you gonna do?
Use a model?
Yeah, I mean, it'd be hard to do, wouldn't it? Okay, well, I'll tell you what, we could do it in this classroom
Yeah.
if we had enough money to spend on a pretty fancy piece of equipment. We could do it right in here. It's pretty amazing.
These old people have fancy pieces of equipment.
Yeah, they did. Actually, they were very good at building apparatus to do things like this. Here's how we could do this. Okay, we knew for a long time, we knew that gravity was an inverse square law. We could see that happening. That was very clear that when you looked at the acceleration that was necessary to make objects go around the sun in uniform circular motion, we knew what the acceleration had to be, and depending on how far away objects were, we could see that it varied like that. No big deal, right? That when you double the distance away, the force of gravity weakens, and therefore the acceleration of gravity weakens by a factor of 4, okay?
Yeah.
We knew that. People could even surmise that, well, it must have to do with the masses of the objects, right? The bigger the masses, the stronger gravity would be, correct?
Yeah.
Okay, and that makes sense, because think what mass really is. Mass, you can think of mass as being just the collection of stuff, right, of matter. You could take a piece of styrofoam that has a mass of 1 kilogram, and you could take a piece of lead that has a mass of 1 kilogram. They're gonna look very different, aren't they?
Yeah.
The piece of lead is gonna be pretty small, the piece of styrofoam is gonna be pretty big. But if we ground those down with a really fine grinder to the point where they weren't even atoms, but they were like subatomic particles, what do you think those two piles would look like then?
Things.
It would look exactly identical, right? Okay, the constituents would have to be the same, right? And so, people had a pretty good idea that that had to be the case. And so, if we double the mass of an object, then it would make sense that the gravitational effect should also be doubled. And people could even, by some observations of, say, looking at asteroids, people could even justify that that had to basically be right, okay? So, we could even say then that if the force of gravity is proportional to 1 over r squared, well, that's like saying that the force of gravity is equal to some constant. Let's call it k sub 1 times 1 over r squared. We could even say that we know that the products of the two masses should act to increase the gravitational force when the masses are bigger, so it probably even looks like this. Make it a new constant, k sub 2 times m1 times m2 over r squared. But we had no idea what that constant was. And the constant was, one thing we did know is that it was a very small number because gravity is a weak force. But didn't know that constant. It'd be hard to determine. But if we did, think of what that would imply. If we knew what the constant was, which we do now, we could do a calculation and find the mass of the Earth right now in this room. It's no big deal. Okay, we know what the radius of the Earth is. People did then too. That's what's interesting. People were able to find the radius of the Earth.
How did they find it?
How'd they do that? Good question.
Fly an airplane on them.
No, they did. People knew this. People knew this long before there were airplanes.
Shadows.
Yes, that's how they did it.
What? That didn't make sense.
I'll show you. Here's how you did it. So here's Earth.
Oh, it's beautiful.
Okay, isn't that beautiful? There's Earth, and I'm gonna put some. Here's what we're gonna do. Here's the experiment that we're gonna run. We're gonna have 3 of us. Let's say is sufficient. We're gonna have 3 of us. We're gonna take some trips. We're gonna keep careful track of the days, and so on a specific day, I'm gonna go to the equator. You're gonna go to a fixed latitude in Europe, and you're gonna go pretty far north, right? And we're all gonna measure what the longest shadow is on that day when we put a uniform stake into the ground so it has a fixed height above the flat ground and it's exactly vertical, okay? Which we can do. That's not hard to do. You can put plumb bobs on the side. You can measure the distances down to the flat ground, in various places, and it's pretty easy to get an almost precisely aligned vertical stick with a known height. We'll measure the shadows in all those places. What does that look like? So, here's one.
I'm at the equator.
You're at the equator, right? Okay, so there's one stick at the equator. There's one stick up here. And here's one stick up here. I exaggerated the scale a little bit. These are pretty tall sticks. But you get the idea. Now, if we look at the shadow that these things cast, this one right here might cast a very short shadow, okay, at this latitude. This one casts a longer shadow, and this one casts a still longer shadow on the flat Earth. Obviously, the curvature is unimportant on these very small scales, right? Well, the rays from the sun are coming in parallel. The sun is a long ways away, 98 million miles away, and these things are separated by a matter of a few hundred miles, it's trivial, right? So the rays are coming in parallel. And so doesn't it make sense that we should be able to look at whatever the length of that shadow is determining what the angle is for those parallel rays at each of these locations, right? And so doesn't it make sense? The geometry is a little bit complicated. We have to know a little bit of spherical geometry, which we don't really know yet, but it's not that big a deal. That by looking at the differences between those shadow lengths and knowing where they are on the planet, how far away they are, we ought to be able to pretty accurately calculate the radius, how curved it is, therefore what the radius is. We could do that. It's not that big a deal. You can kind of see how that would be that big a deal to do, probably, right? So people were smart.
Yeah.
They found a way to do it. But think about this now. What if I took an exactly, very accurately measured mass of 1 kilogram, and the weight is 9.8 newtons, right? We can use any units we want to. We know the radius of the Earth. What if we knew what this constant was? What would that imply? So let's put all these pieces in the puzzle here. So we've got a weight of 9.8 newtons is equal to K2, which pretend we know, times 1 kilogram divided by the radius of the Earth, which is, I think it's like 6, I don't know if it's 6 or 6 point, I think it's like 6 million meters. Look it up real quick. 6 times 10 to the 6
Wow,
meters,
life
I
is
think.
so hard right now.
Wait, where'd you get the 1 kilogram from?
Because that's what we chose, a 1 kilogram mass
Okay.
has a weight of 9.8 newtons, right?
I want miles.
We want meters.
Yeah, what is this? In meters. 6.371 million.
Okay, so. Okay, times, the only unknown would be the mass of the Earth, if we knew what that was, right? Agreed? So do you see that finding the value of that constant would have been identical to measuring the mass of the Earth? It would have made it trivial for us to find the mass of the Earth, right? So that's a pretty big deal. If we could find that elusive value of that constant, we could do it. Well, Henri Cavendish did it. Here's how he did it. He built an apparatus where he suspended from a long piece of wire, he suspended a carefully balanced arm, and at either end of the arm, he had a sphere of lead. Now, what he was able to do then is he was able to very carefully calibrate this. He would drop electrostatic charges onto the lead, and he would bring some other electrostatic charges close to this thing, fixed distance away. That's a very easily calculable force then acting. You know, we knew quite a bit about that stuff at the time. So he could know how much force was attracting these charges, and he could see how much this wire was deflected by known forces, right? Very, very small forces. And so by just changing the forces, he could measure what the corresponding deflections were of the wire, right? So imagine like when you have your shoe, it's hanging by a shoelace and you spin it and it travels in one direction, then eventually it slows down and spins back to it. Same deal, right? Same kind of thing going on. And then to be very precise, he would shine a light on this thing, and then the light would reflect off a mirror over to the wall, so he could see that when it turned very slightly, you could read, far away, you could read that slight deflection by where the reflection was on the wall. Does that make sense? So then all he had to do was take 2 other spheres of lead, larger ones, of known mass, and move those things in unison together towards these other spheres until he witnessed some deflection. And then all he has to do is measure very carefully how far apart the centers of mass are. He knows what the 2 masses are. He knows the radius of the Earth, a good estimate of the radius of the Earth, and he knows how much force it takes to deflect that arm, right? So if you look up here at that equation then, what are all the things that numbers we could plug in? Whoops. We know this, right? That's the deflection, that's by the calibrated force, what do we call this? Force scale, right?
Uh-huh.
Because we know how far it deflects corresponds to the force, gravitational force. He knows the masses of the objects that are exerting the gravitational attraction. He knows the radius of the Earth, right? And so what's the only unknown? Gee, he solved it. He found the universal gravitation constant to within like, I think it was like to 4 sig figs. It was pretty good. And so then that allows us to find the mass of the Earth, right? Pretty amazing that you can do that, all in a lab. I'm always just, human ingenuity is incredible to me that you can think of a way to do that just from within a single room. That's pretty incredible. You have to do anything outside. We could do it all, never leave the room, and we could find out what the mass of the Earth was. Incredible. All right, so I gotta take roll. It's a good place to leave off.
It's crazy.
Isn't that crazy? Oh, and